Thank you. Can you hear me? Because I cannot see you because of the light. So I'm going to talk about Akka Streams. Who has already used Akka Streams? A couple of you. Great. I will show you some basics and some more advanced things. And I promise I don't want to be the one who is between you and the beers, so I will finish timely. Okay, so what I have just shown you is this fantastic program. This is obviously printing Learn Your Akka Streams for Great Good. In a weird way, each line is indented a little bit more, and printing happens character by character. And let's take that example, or I will take that example to show you how to use the Akka Streams API. Akka Streams, as you might know, is an implementation of Reactive Streams. Reactive Streams is a specification which probably makes it into Java 9, and that covers stream processing, obviously, but with asynchronous and non-blocking back pressure. So back pressure is the big thing that prevents faster producers from overwhelming slower consumers. Okay, Akka Streams is an implementation of that API, or sorry, of that specification, and we are going to look at one part of the API of Akka Streams, which can be used to define linear streaming or stream processing topologies. So essentially pipelines of stream stages. And in that API, in that part of the API, those stages are essentially blocks which have either an outlet, then they are called sources, or just an inlet, then they are called sinks, or they are the things in between, which are called flows. They have an inlet and an outlet. So let's start with a source, a very simple source, and we should pick the Akka Streams Scala DSL, not Java DSL, because this is Scala Swarm and not Java Swarm. So from the source singleton object, we can, for example, use a source single factory, which creates a source which only ever emits a single element. And if you look at the type of this thing, we will see that it is a source of string and not used. Just ignore the not used, the second type argument for the time being. We will get to that later. So now we have a source that emits strings, well, a single string. And in order to build a stream processing topology, we need to feed that source into a sink. Yeah, great. So we use the to combinator, which accepts a sink, as you can probably guess from the graph sink shape thingy here in the type signature. So let's feed it into a sink, sink dot, what's wrong here? Come on. For each, and it's even not there, so we import it. Hello. Here we go. For each, print ln. All right, great. Now, what is the type of this thing? As you can see here, it is a runnable graph of not used, but just ignore the not used. A runnable graph is something that can be run, obviously. And in Akka Streams terminology or vocabulary, this is called materialization. So there is a run method. And unless you run it, nothing happens, okay? So these sources and sinks and even the runnable graph is just a blueprint. It's just like a blueprint of the stream processing topology. It's cold, it's not hot. And to make it hot, to make elements flow through the graph or through the graph stream processing topology, we have to run it. And now we should run it and hopefully see, learn you Akka Streams for Great Good. Okay, so we are getting closer to this output. But of course, a single is not enough. And one more thing I would like to point out is this process hasn't exited yet. As you can see here, it's still running. Why? Well, we have started an active system initially because when we run a runnable graph, the materializer, which is an implicit argument to the run method, and which we have created up here, maps the blueprint onto actors, because this is Akka, right? So Akka is an implementation of reactive streams by means of actors. Okay, so we have some actors running, we have an active system, we have dispatchers and threads, and we need to shut down that. But when? We don't know when this is done, okay? Because that happens asynchronously. The materialization happens asynchronously. So actors are performing their work, and we need a way to find out when this is done. And now it's time for the materialized values. Materialized values are, a way to interact with a running stream. Whenever you run a stream, each stage in the stream produces a materialized value of a particular type. And that's the reason why there's a second type parameter for all of those stages, for the sources and sinks and flows, and for each stage, there is a type parameter. Now this source single, let me show that again, has a type a parameter of type not, sorry, a materialized value of type not used. And that's more or less like unit. And I think we only have not used because of the Java API of Akka. So the meaning is this is not an interesting materialized value. Okay, but let's take a look at the sink for each. That is a sink accepting any value, type T. We could be more strict, sorry, and say we want a string here. Then we have a type of sink string future done. And the future done is the type of the materialized value. So when we run this graph, this sink for each gives us a future of done. And done is also almost like unit, so the interesting information here is the future. So when the future is completed, we know that this sink has completed. And that sink only ever completes if the whole stream has completed, either normally or by failure, okay? So we just need a way to get that future of done. Unfortunately, when we use the to combinator, we don't get it. We still have a runnable graph of not used, and that is because if we use to, only the materialized value of the upstream is kept, and the downstream, the right-hand side, so to say, is dropped. So we can use toMat, that's a different combinator, and now we have to specify which materialized value we want to keep. So let's say keep both, left, none, right. In this case, we are interested in the right one, okay? And if we take a look at the type now, it's a runnable graph of future of done. Hooray! So from the run, we get the future of done, so we can now do on complete. We don't care whether it's a failure or a success. We just shut down the system. And we need, what do we need? Yeah, the execution context, thank you. The dispatcher for the onComplete. And now if we run it again, hopefully this works by this button, we will see it started and finished. Hooray! Mission achieved. Okay, so now let's get back to our example. We want to print this line 7 times. So instead of a source single, we go for a source repeat. And there's so many sources, but repeat looks like a good candidate here. But this, of course, will run forever, because streams potentially are infinite. So they can run and run and run, and we'll never complete. We only need 7. Any suggestions how to take 7? Take. Good. So the API looks a lot like the collection API. Streams and collections have something in common, but they are different things. So with this approach now, we are getting even closer. Okay. The next thing we should do is indent each line by its index, starting with 0. Okay? How could we achieve that? How do we know the index of an element? What we can do is we can zip our source with another source. So we can say source dot from iterator and just create an iterator from 0. Okay. And what that gives us now is a source of string int tuples. Great. Now, with those string int tuples, we should do something. So we should now map those. Case, string, n. Okay. Just for the compiler to be happy, let's emit the string here. We could now, and that's one of my favorites, multiply. So to calculate the indentation, we multiply the space times n. So in Scala, you can really multiply strings. Isn't that awesome? I love it. And then we just return this indentation, and then the string itself. That should give us indented strings. Hooray! Almost there. What is missing is that we want to print character by character. And we also want to throttle the speed. That was much too fast. And by the way, there's an easier way to express that. We could zip with index. There's also a method called zip with index. And that should give us the same effect. But I think this is a long now. And I cannot multiply with long, so I go back. Okay. So what we want to achieve now is character by character. Now, in Scala, a string is a sequence of characters. And there's another combinator here, another built-in stage. It's called map Concat that expects not a single element, but a sequence or an iterable of elements. So we can say map Concat, and as you can see here, just could see here. That works. Okay, guys, help me. What's wrong? I have to go here and look at a proper error message. Yeah, maybe the string is no longer string, but a char. Thank you. So let's get rid of the string here, and we are fine again. As said, a string is a sequence of characters, and implicitly Scala treats this string as a sequence of characters now, because we're using map Concat. If we run that, we will see a subtle error. Every character is print ln. Okay, so let's change that and just print. And also, let's add the, missing new line character. Yeah, that looks good, but too fast. So last thing we introduce is the throttle stage. With throttle, we can define that we want to have, let's say, 42 elements per second. 42 is always a good number. For this to work, we need to import Scala concurrent duration int. Yeah, okay. So 42 per second with a maximum burst of 1 or whatever, doesn't really matter here. And the throttle mode, shaping. Enforcing would fail the stream, but we want to shape it. We really want to, well, shape it to 42 characters per second. And if we run that now, we are hopefully seeing, yeah, what we did before. Okay, cool. Now what I have shown you here is a very simple stream processing topology. We have seen how to write a linear stream processing topology using sources and sinks and built-in stages. And we can even take this apart and not really run it here. I will just jump to a particular state here. Yeah. To the head. So what we can also do is we just take those parts apart. No, take the whole thing apart. And for example, define a source that is called 7 lines. That's just source repeat 7. Take 7. As you can see, it's a source of string and not used. Then here we define a flow. That's the thing that has an inlet and an outlet. So it accepts strings and produces chars. And here we define a sink for chars. Okay? So we have 3 reusable blueprints. We can freely share and reuse. They are immutable and shareable. And we can combine them using via, using tomat, and we can run it. Okay, so that's the part of the API that you probably use 80% of the time. Any questions before moving on? Okay.
Thank you for your talk. It's not actually a question. I just wanted to mention that you don't need to import seconds explicitly. You can just run the smart completion.
Here?
Yep.
Oh, so I don't need this?
Yep.
Uh-huh. Where?
Oh, okay. No. Print, for example, 1.sec. No, remove
okay,
seconds.
Maybe we'll do that later. Thanks for the hint. Yeah, if you could show me later, that would be really nice. So that was the linear API, so to say. I want to move on and show you how you can build arbitrary graphs, almost arbitrary graphs, which can have cycles. Okay, so you're not restricted to those boxes which have single inlet outlet. You can define your stream processing stages that have, let's say, 1 inlet and 3 outlets, or 2 inlets and 4 outlets, or whatever, and you can combine them as needed. It's important to understand that in order to have a runnable graph, you need to connect all the inlets, outlets. There must not be any open ends. The example I'm going to show you is an access log. It's an access log for Akka HTTP. I don't know whether you're familiar with Akka HTTP or not. In a nutshell, what you do is you have the HTTP API. To define a server, you invoke the bind and handle method, and you specify a route. And a route is usually defined using those directives. But if you look at the signature of the bind and handle method, you see that you have to provide a flow from request to response. And that's pretty obvious, right? HTTP server produces responses when requested. Okay? That's what you have to provide. And what Akka HTTP doesn't give you is an access log, because it's not a HTTP server, it's a library which you can use to build a HTTP server. The demo here is using the with access log method that we have to implement, and I will implement in a minute. And there you define an access log, and that is just a sink for enriched request and response pairs. Okay, so you get a request and a timestamp, and you get a response, and then you typically have all you need for an access log. So you can log the HTTP method, the path, the status code, like OK or not found, and the time it took, okay? So that's typically what you want to see in an access log. In order to implement that, we have to define a stream processing topology that looks like that. You remember, we have to provide a flow from request to response to the bind and handle method, okay? So this is a box with an inlet and an outlet, so it's a flow. And it takes requests and emits responses. And this is what we are going to write as a graph. And we wrap the route handler, which has been defined here in this example, in this demo. We define the real handler. We wrap the real handler within a graph that looks like this. So first, we have a stage that enriches the request. For example, by adding a timestamp. So we get a tuple of request and timestamp. And then we fan out. We have an unzip stage that takes this tuple, feeds the request into the normal handler, and feeds the enriched request to this other stage. The handler here produces responses. The responses are broadcasted. That's again a fan out here to the outlet of the flow and to the zip. So this zip here gets the enriched request and the response, and that is all it needs to feed it into the access log. That is a sync, and that can print the desired access log, for example. So the types in question are access log, that's just a sync of an enriched request, a tuple of HTTP requests and some arbitrary A, and response. And a handler is just a flow from request to response. All right, so how do we implement that? The blueprint looks like this up here, okay? That's what we have to implement. So first of all, we have to use the graph API. So no longer flow sync source, but also the graph DSL. There's a create method. We need to feed in the access log, and now we have to specify a function that creates our graph, and this function takes an implicit builder. And it also takes the access log, which we have fed in. Make the compiler happy, yeah. So we have to return the shape of the graph, and the shape is a flow shape. And the flow shape has an inlet and an outlet. We don't know the values yet, okay? So that's just the plumbing, I would say, the boilerplate. And we need to fill that first with a stage that enriches request, okay? So the request is enriched by applying that function here. So we define a enrich request stage equals builder add. So we need to add each stage to the builder. The builder itself is mutable, but at the end of the section here, it produces an immutable blueprint. So it's only internal mutability. So we add, yeah, exactly. So we want to enrich the request. So we have a flow of HTTP request. And we map, we call map, and the request gets enriched to tuple by applying this function. Okay? So if you look at the type here, you now have a flow shape of HTTP request goes to HTTP request and A. That could be the timestamp or some other thing. Okay? With that knowledge, we already know that we want to connect this with the inlet. Okay? The next thing you need to do is the unzip stage. Here, we want to unzip what we have seen as the output of the enrich request. So how much time do I have left, by the way?
You have all the time you need. It's just how people are going to be angry. Okay, let me just check, sorry.
Don't worry. I'll continue.
Just continue.
Okay. So we want to add an unzip. And sorry. And with that, we can go to the real nice graph DSL part. Of course, we could use the builder, and in addition to just add some stages to the picture, also add the connections, add the edges. But there's a very nice operator syntax to do that using fancy arrows. And as I can see, I only have 5 more minutes. Oh, okay, cool, great. Thank you. So what we want to do here is, from this enrich request, go to unzip. Okay, so we just say enrich request dot out. That's our outlet that produces these tuples of request in A, and we connect it with our unzip, and that does not compile. I know why. We have to import graph DSL implicits. Hooray! And it still does not compile. So I did something wrong. Okay, signature-wise, and I think that might help. Thank you. Because we want to connect it with the inlet of unzip, of course. Okay? So that is our first connection. The next thing we want to do is we want to feed one outlet of the unzip into the handler. So unzip dot out 0 or out 1. In this case, I would say out 0 because that produces a request. So we feed that into the handler. All right. And from the handler, we want to go to this stage, broadcast request. Okay, we need to define that. So we add the builder. We add a broadcast of HTTP response, which has 2 outlets. And we can now connect the handler with the inlet of the broadcast request. We're getting closer. So this now needs to be connected with the outlet of the flow shape and also with another stage, zip. So let's do this first, broadcast request, out 0. And then we need a zip. And that takes an enriched request and the response. So what we can do now is broadcast request zip dot in 1. Hooray. The zip also is fed from this unzip here. So let's add this edge, unzip dot out 1. That's the outlet that, it only produces an A. It should produce a tuple of HTTP requests in A. So this won't compile because I made a mistake. So this should not compile. Yeah. Damn. So the mistake was here. I have to enrich it in a different way. I need to have more. I need to have a nested tuple here, something like this. Okay. No, still not. Okay, the request has to be. Okay, I screwed things up somehow. But you know what? Sorry for that. Oh, why does that not work? I'm in the wrong one here. Git to the rescue. Git o dot, git o master. Somehow I screwed things up. Oh, it was the wrong order. Damn, I almost got it right. Okay. Tuples are too crazy. Sorry for that. So yeah, but as you can see, it's really almost the same. So we connect the unzip out one with the zip in, and the missing thing, which I haven't shown you before, was we want to feed the output of zipping together the enriched request and the response into the access log, and then we are done. And just so you can see that this is really working, let's just run the demo here. And in this case here, we, yeah, just run the demo so you will see that it's working. Things are printed. So it's listening, and localhost 8000 test. Okay, so it seems to work here, and in the output here we have our access log, HTTP method, URI or path, and so on. Okay, so with this really couple of lines of code, I mean the real code is these 10, 12 lines of code. You can write your own access log for Akka HTTP based servers, and because we are all lazy, I have provided that as a library. It's called Accesses on my GitHub repository if you're interested. So this is a graph. You have now seen the graph DSL. It's not a too complicated graph. It's not a linear one, but the fan in and fan out is still basic, and it does not have any cycles. So it's not super interesting, right? So last thing I want to show you, not in too much depth, is how you can write graphs which have cycles and a little more. And as a quick motivation, I have to stop that first, sorry. As a quick motivation, I'm going to run a server here. It's a server that serves server-sent events. So let me quickly show you what that means. So when we send a GET to that server, we get back service-sent events. Who knows service-sent events? Only a couple. It's almost like WebSockets one way only. So it's a way for the server to push data, to push events to the client, to the browser or whatever client, okay? It's a standard, it's a W3C standard. It's more lightweight than WebSocket, so if all you need is server to client, that's maybe preferable over WebSocket. Anyway, it's a standard. It has just been merged into Akka HTTP, by the way. So this one gives you the ability to get, as you can see, 10 events. Service and events also has the notion of a last event ID. If you set this header, the server can pick up the last event ID that was seen by the client and continue with further events. Okay, but this server stops after 10 events. And this is only to simulate that the connection could drop for various reasons, because the server has no more events yet right now, or, well, maybe there was a connection problem. If you want to have a reliable, consistent, or continuous connection, you have to reconnect if the connection drops, right? And in Alpaca, which is a really awesome project under the Akka umbrella, we have implemented an event source, which is such a continuous source of service and events. So what you provide is a URI, a way to send requests to the server, an optional last event ID, and a retry delay. So what this thing will do, it gives you, well, an event source. That's, well, okay. So an event source is a source of service and event, okay? It gives you an event source, and once the connection drops, it will reconnect, and thereby setting the last event ID header. So the code looks, or the code is using a graph with that topology. So as you can see, this is a box with one outlet, therefore it's a source. There's a trigger, there's a merge, then there's a stage that connects to the server and unmarshals the response, which is a HTTP response, which essentially has bytes into those nice service and event case classes. And then it broadcasts those. They eventually go out of this box. But there's a feedback loop. So every time this connection or a connection is terminated, a delimiter will be introduced, and using that delimiter, the last event ID is recalculated, and another request is sent. So this is a graph which includes a cycle, and I just want to show you how this can be implemented. So it's not 10 lines of code, it's a little more, but not so much more. And the really interesting part is this one here, the source from graph and so on. It's a cycle, which I think beautifully can be, which is using the operator notation again. And what I really like about that is that you can visualize the cycle using the reverse operator, the arrow to the left. So it goes from trigger to merge, to continuous event, broadcast, events, and then it goes back into merge. So you can really see that a cycle is happening here, right? If you're interested in some of the advanced features here, there's a couple of things like recovering, like, well, some of the more advanced functions like sliding, scan, and so on. Just take a look at the code. It is part of the Alpaca project. This is what I wanted to show you, and I think there's still time for 2 or 3 questions, and then we run for beer.
Hi. Looks really, really interesting, and the DSL is actually, like, I think it's really, really cool. But as a beginner, let's say that I were to write from line 111 to 122, that to me looks very complicated, like as a newcomer. How do you go about debugging, for example, the stages? What if I wanted to, say, put a breakpoint at some point? Would it work, or do I just have to rely on prints?
Okay, so this is all asynchronous code, and I think I haven't used a debugger on asynchronous code for the last 2 years. I know that Julian, who's not here, has written asynchronous debugger for Eclipse, but I'm not on Eclipse. And no, so I think it's in general it's super, super hard to debug any asynchronous code. So if you use Akka or Monix or RX or whatever, everything that is asynchronous is hard to debug. And here it gets ways harder, because this is just a blueprint. This is not even running at all. So I think you cannot set breakpoints here. You just cannot, okay?
I think the answer is that you debug it by thinking.
Yes, of course. Yeah, and you can put your println everywhere, of course. A great way of debugging. And but let me get back to what you said initially. Yes, this is the complex part of the DSL, the graph DSL. So hopefully I didn't shock you. And if I shocked you, just go back to this one here, and that's the really simple linear step-by-step DSL for writing those linear stream processing topologies, and that is what you usually need as an application developer. If you want to write a library or some more advanced things, then sooner or later you will have to write a graph, but not necessarily the very complicated one here. Maybe one like this here. Okay, but yeah, the Flow API is the simple one, and as a beginner, you would start with a linear Flow API.
Yeah, debugging is one thing here, but how to test it?
Testing is not too hard. No, honestly. So if you define a flow, or if you define a sink or a source, I can show you the test code for this, for example. Here's a specification. So this tests all that needs to be tested. So essentially, you define a runnable graph. So in this accesses here, what we do is we define a flow. So in order to know what the flow is doing, we need to provide a source with known test data. We feed into the flow, and we need to provide a sink that inspects what's getting out of the flow. Okay, so testing is not too hard. Whatever you want to test, whether it's if you want to test a sink, you need to provide the test data via source, or vice versa. And there's even the Akka Stream test kit. So if what I just mentioned is not enough, you can find in a very detailed way, say, okay, now push the next element into the stream, and now I expect an element being emitted from the stream. So with this Akka Stream test kit, I think you get all you need for testing your graphs.
Last chance for the last question of the day. There we go.
I'm just curious, how much is it different to other streaming frameworks on the market? Say, Spark Streaming, Apache Flink. Well, I will make it more concrete in terms of what's happening under the hood and in terms of possible applications.
The two you just mentioned are distributed streaming solutions. Spark Streaming is not streaming at all. It's micro-batching, so it's a lie. Apache Flink is streaming first, so they fully embrace streaming in a distributed fashion. I'm not totally aware, or I don't know about the details. In Akka Streams, you have Reactive Streams implemented, so you have asynchronous and non-blocking back pressure. I don't think Flink has that at all. I'm not quite sure. There's another difference. This is for local streaming, not for distributed streaming. And there's a couple of other things like Monix, like Swave, like RxJava. They are all in the same space like Akka Streams, and so you can really compare those. And under those, Akka Streams has probably the richest API. Others have not the ability to define not all of them, circular graphs, but some of the others have maybe an even easier to understand or to learn API. So that's the difference, I would say.